So here we are again, gonna do some stats. Hope y'all had a lovely 3-day weekend. You gotta have some time to relax. Hopefully there wasn't a whole lot of schoolwork to get caught up on, as we've only really gotten through 1 week of full classes. So hopefully your teachers aren't bombarding you already. But we are gonna just jump right in today. We're going to do our lesson on section 6.2 today, and then tomorrow we'll do some practice problems with that. For tomorrow, I've got a Desmos activity that I've made. We'll see if that works any better than the Pear Deck activity. Just gotta change things up, try different things. So that's the idea for today and tomorrow. So if you have stuff that you're writing notes in, please have that available. We're going to have some things to add. The good thing about this section is that it is very similar to stuff that we covered in a previous chapter. We're just applying the same concept to a new set of context. So that should be hopefully a little bit helpful. Be going over something that we've already seen. So there you go. So we're going to get started. Get all my little clickety clacks in order. So here we are, still in chapter 6, random variables. We're moving on to section 6.2, transforming and combining random variables. So here we go. Come on. So what we're going to hopefully learn today. We're going to learn how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We're going to find the mean and standard deviation of the sum or difference of independent random variables. And we're going to find probabilities involving the sum or difference of independent normal random variables. Super exciting. All right. First, in section 6.1, we learned that the mean and standard deviation give us important information about a random variable. In this section, we'll learn how the mean and standard deviation are affected by transformations on random variables. All right. In chapter 2, we studied the effects of linear transformations on the shape, center, and spread of a distribution of data. Recall that adding or subtracting a constant a to each observation adds a to measures of center and location, does not change the shape or measures of spread. All right. Also, with distributions of data, multiplying or dividing each observation by a constant b multiplies or divides measures of center and location by b, and multiplies or divides measures of center by the absolute value of b. So when we're considering measures of spread, such as standard deviation, interquartile range, things that measure the variance of a distribution, we multiply or divide by the absolute value. So if we have a negative number that is we're multiplying by, we're just going to multiply by the absolute value of that when calculating the measures of spread. Measures of center and location, mean, median, percentiles, quartiles, those just get multiplied by whatever the value of b is, negative or positive. Okay, and again, the shape does not change. So this is from chapter 2, the results that we saw about dealing with distributions of data. So then let's look at some examples. We've got Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle holds up to 6 passengers. We're going to define the random variable x as the number of passengers on a randomly selected day. So x can have the value of 2, 3, 4, 5, or 6, and we have our probabilities of each of those numbers of passengers occurring. And then we have our histogram showing the passengers and probability for right here. All right. With a little bit of calculations, we can determine that the mean of the random variable x is 3.75, and the standard deviation is 1.090. We can do that by hand, or we can do that with technology. That is up to you. Pete charges $150 per passenger. Right? The random variable c describes the amount Pete collects on a randomly selected day. So the random variable c can have values of 300, 450, 600, 750, or 900. And we can obtain those simply by multiplying the number of passengers by the cost per passenger. And there we have our possible values. The probabilities of each of the possible values matches the probabilities of the number of passengers that get us that amount of money collected. Right? We don't have to recalculate any probabilities, they just kind of transfer over. Right. And so this is a transformation through multiplying by a constant, multiplying by $150. If we look at the histogram of this probability distribution, we get the same looking histogram as we do up here. The only difference is the values on our horizontal axis, right, is now money collected instead of number of passengers. So the numbers changed along the bottom, but the height of the bars did not. Right. It's the same, nothing has changed with the shape. Right. The mean of C is 562.50, and the standard deviation is 163.50. Right. We've already compared the shape, center, and spread. Well, based on what we already learned from distributions of data, when we multiply by a constant, we multiply the mean and the standard deviation. They both get that multiplier. Right? So the new mean of C is just 150 times the mean of X. The standard deviation of C is 150 times the standard deviation of X. Right? We could go through all the same calculations and manually determine the mean and standard deviation. However, because this random variable C was created by transforming X, we can save time by just knowing, hey, I just gotta multiply, right? Less calculations, less time, happier people. So here we have, in summary, multiplying or dividing each value of a random variable by a number b results in, we multiply or divide the measures of center and location, mean, median, quartiles, and percentiles by b. And we multiply or divide measures of spread, range, IQR, and standard deviation by the absolute value of b. Obviously, in our example, we don't need to concern ourselves about the absolute value of b. We're dealing with a positive number. There's no adjustments for that. And again, this does not change the shape. We saw that in the probability distribution with the histogram. The histograms look the same. As with data, if we multiply a random variable by a negative constant b, our common measures of spread are multiplied by absolute value of b. All right, so we just did multiply. Now we're going to add a constant. So again, consider the same context with Pete's Jeep tours. We previously defined C as the amount of money Pete collects on a randomly selected day. And this is the same probability distribution, mean, and standard deviation that we had on the previous slide. Now, it costs Pete $100 per trip to buy permits, gas, and a ferry pass. The random variable V describes the profit Pete makes on a randomly selected day. So we get from money collected to profit by subtracting $100, right? 300 to 200, 450, 350, and so on. And once again, the probabilities simply transfer from the money collected amount to the profit that corresponds to it after subtracting $100. Once again, we get the same exact looking shape with slightly different numbers on the bottom for the profit. Now we get the mean for V as 462.50, exactly $100 less than the mean of C. right? And the standard deviation is 163.50. It's actually the same. Right? We get the same standard deviation. Now this makes sense because if we look at our distributions, right, the spread or variance within these two histograms or these two distributions here is the same. The difference from 300 to 900 is the same as the difference from 200 to 800 or 200 to 350, right? We're making the same incremental increases. So our measures of spread are going to stay the same. The only things that are going to change is the measures of center, right? Because essentially we're taking the histogram and we're just shifting it down the axis or shifting it up the axis if we're adding or subtracting. Other than that, the width is not changing. Is there anything I can clarify about that? Right. See, we need a moment to write anything down from this screen. So then we get the following conclusion. The effect of a random variable of adding or subtracting a constant. We get adding the same number a, which could be negative, to each value of a random variable. In the context we just saw, that is a negative number we're subtracting. Adds to measures of center and location, mean, median, quartiles, and percentiles. Those all shift, but does not change measures of spread, the range, IQR, and standard deviation. Right? Also, does not change the shape of the distribution, which we visually have seen in the last few examples. The shape is staying constant. So between multiply, dividing, and adding, subtracting, we have a linear transformation. The effect on a linear transformation on the mean and standard deviation. We have if y equals a plus bx, hence this is why they call it a linear transformation. It looks like y equals mx plus b. This is a linear transformation of the random variable x, then probability distribution of y has the same shape as the probability distribution of x. The mean of y is equal to a plus b times the mean of x. The standard deviation of y is equal to the absolute value of b times the standard deviation of x. And again, we use absolute value because b could be negative, and we cannot have a negative variance or negative standard deviation. We have to be a positive distance away from the mean. Linear transformations have similar effects on other measures of center or location, median, quartiles, percentiles, and spread, range, and IQR. Right, so if you were asked in some question to not just determine the mean, but maybe find quartiles or percentiles, or maybe the median is the measure of center being used, right? And you have to adjust that. You're going to follow the same rules. Right, whether we're dealing with data or random variables, the effects of a linear transformation are the same. So you don't have to remember different rules for whether we're dealing with data set or random variables. They follow the same rules when it comes to linear transformations. Note, these results apply to both discrete and continuous random variables. So again, it's one set of rules, okay, which is kind of nice. Right. So we've done transformations, now we're going to go to combining random variables. There are many interesting statistics problems that require us to examine two or more random variables. So we're going to investigate the result of adding and subtracting random variables. For these examples, we're going to let x equal the number of passengers on a randomly selected trip with Pete's Jeep Tours, and y be the number of passengers on a randomly selected trip with Aaron's Adventures, another tour company that is located elsewhere. We're going to define t to equal x plus y. In other words, t equals the number of passengers on a randomly selected trip between both tour companies. what are the mean and variance of T? Okay. So we have our provided information, the same probability distribution from the beginning of the example, where we are looking at passengers and probability. We had a mean of 3.75 and standard deviation of 1.090. And here's our histogram. And then for Erin's adventures, notice that she has less variability in the number of passengers, so to say. She can only have from 2 to 5 instead of 2 to 6. And obviously the probabilities are slightly different. The fact that these are not the same size sets, right? There's more options in X than there are in Y. Doesn't really matter. We can still combine these things. All right. We have a mean for Y of 3.1 and a standard deviation of 0.943. Right. All right. So first, how many total passengers can Pete and Erin expect on a randomly selected day? All right. Pete expects 3.75 passengers and Erin expects 3.1 passengers. They will average total of 3.75 plus 3.1 equals 6.85 passengers per trip. Can generalize this result as follows. The mean of the sum of random variables. For any two random variables x and y, if t equals x plus y, then the expected value of t is the expected value of t equals the mean of t equals the mean of x plus the mean of y. Right? In general, the mean of the sum of several random variables is the sum of their means. Right? So whether I'm adding just 2 random variables or 10 random variables, if I want the mean of the sum of those things, I just add up the different means. Right? There's no tricky calculation or anything, you just add them up. Right? How much variability is there in the total number of passengers who go on Pete's and Erin's tours on a randomly selected day? Well, to do that, we need to find the probability distribution of T, right? Because that probability distribution has a whole different set of possible outcomes, right? Depending on the different combination of number of passengers between the two tour companies. So that's next. So then the only way to determine the probability for any value of t is if x and y are independent random variables. Right? If they're not independent random variables, then I can't determine the probabilities. Just won't work out. Right? So if knowing whether an event involving x alone has occurred tells us nothing about the occurrence of any event involving y alone, and vice versa, then x and y are independent random variables. So it's basically the definition we've heard of independence previously. Right? If knowing a certain outcome occurred affects the probability of another outcome, then they're not independent. We want these to be independent in order to calculate probabilities. Probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. We should always ask whether the assumption of independence seems reasonable. In our investigation, this example, it is reasonable to assume x and y are independent since these two companies are owned by siblings. That was part of the context not provided. Operate their tours in different parts of the country. Right? Because they're in different parts of the country, if someone signs up for Pete's tour, it has no effect on someone signing up for Erin's tour because they're not taking people from each other's tour companies. They're not pulling from the same population. Right? So again, we need to make sure the assumption of independence is reasonable. In this case, it is, so we can move forward. So then we have to consider all possible combinations of values x and y, meaning all different possible combinations of passengers from Pete's and Erin's. Right? So like if we look at the first row, this is the possible combination of 2 passengers from Pete, 2 from Erin. We get a total number of passengers of 4. And the probability, because these are independent events is probability of 2 passengers times the probability of 2 passengers, 0.045. And we move on down the line using the same logic. And we create all the different combinations. We can have 2 and 2, 2 and 3, 2 and 4, 2 and 5, 3 and 2, so on and so forth. And we get multiple different ways to have, 5 people, 6 people, 7 people, 8 people, 9 people, 10 people. Only one way for 11. All right. So we get these different outcomes, and that builds our histogram. All right. Now recall that the mean for t was 6.85. And that absolutely makes sense given our distribution here. That looks about where the center should be. The variance, right, based on our formula, t will be each possible outcome of t minus the mean of t squared times the probability of each of those outcomes occurring. We add all those up. This calculation would look like this if we wanted to write it all out. We get 2.0775. This could take a while. However, we do have the following, right? The variance of x, which we got by just squaring the standard deviation of x that we had from the previous slides, is 1.1875. And the variance of y, using the same method, squaring the standard deviation, we get 0.89. 1.1875 and 0.89 equal 2.0775. All right. So I can actually, knowing that these are independent random variables and that I'm adding them up, I can determine the variance simply by adding the variances of those independent random variables. Save some time. I don't have to do this calculation unless I really want to. Okay. So then, as our example illustrates, when we add two independent random variables, their variances add. Standard deviations do not add. We do not add standard deviations. That is not possible. We have to add the variances, take the square root of that, and we get our standard deviation. So we get this concept, right? The variance of the sum of random variables for any two independent random variables, again, independent, x and y. If t equals x plus y, then the variance of t is the variance of t equals variance of x plus the variance of y. In general, the variance of the sum of several independent random variables is the sum of their variances. So again, if I have two random variables that I'm adding, or 10 random variables that I'm adding, I can determine the variance of that sum by adding the variances of each individual independent random variable. Once again, remember that you can add variances only if the two random variables are independent, and that you can never add standard deviations. Okay, don't do it. So we can do a similar type of example if we wanted to determine what happens when we define a random variable as the difference of two random variables. However, to save some time, we have the following summary. The mean of the difference of random variables is somewhat what we would expect it to be. For any two random variables x and y, if d equals x minus y, then the expected value of d is the mean of x minus the mean of y. So we just subtract the means in the order they were defined by the variable. In general, the mean of the difference of several random variables is the difference of their means. The order of subtraction is important. And just like in many other math applications, the order in which you subtract changes your result. Right? 5 minus 2 is not the same as 2 minus 5. The order matters. So we must do things in the order that they're defined. In this case, it's d equals x minus y. So we subtract the mean of x from, or we subtract the mean of y from x because it's that order. If it was defined as y minus x, we do mean of y minus the mean of x. We have to pay attention to the order. We also get the following result for variance. For any two random variables x and y, if d is defined as x minus y, then the variance of d is variance of x plus the variance of y. This is not a typo. This is the way that it works out. All right. Even when subtracting random variables, the variance is determined by adding the variances of the different independent random variables. Right. So when you're subtracting, that means subtract. Right. If you're adding or subtracting, variances add. Right. So in general, the variance of the difference of two independent random variables is the sum of their variances. Right. But do pay attention here. This is two independent random variables. So now we've done transformation, combining, and the last thing that was on our list of objectives. What happens when we combine normal random variables, and what kind of probabilities can we calculate doing that? Right. If a random variable is normally distributed, we can use its mean and standard deviation to compute probabilities. Hooray! Right. Any sum or difference of independent normal random variables is as also normally distributed. Right. And this makes sense, all right, because as we've seen in our previous examples, shape stays the same no matter what we're doing, right? How we're combining or whatever, or not combining, but transforming and such doesn't change the shape, right? When we combine normal things, they stay normal. Mr. Starnes likes between 8.5 and 9 grams of sugar in his hot tea. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with mean 2.17 grams and standard deviation 0.08 grams. If Mr. Starnes selects 4 packets at random, what is the probability his tea will taste right? All right. So we have a random variable that is normally distributed, and we have the mean and standard deviation for that. So we're going to let x equal the amount of sugar in a randomly selected packet. All right. Then t, right, the sum of the sugar in the tea, equals the first randomly selected packet plus second randomly selected packet, and so on and so forth. All right, so we add the 4 random variables, which is all the same random variable, it's just different occurrences. We want to find the probability that t is greater than or equal to 8.5, but less than or equal to 9. So to find the mean, we add the mean of the random variables, which is just the same mean 4 times. 2.17, 2.17, 2.17, and we get 8.68. We then add the variances. Right? We're adding the variance so that we can then get the standard deviation. We weren't provided the variance, but we do know that the variance is the square of the standard deviation. We have the standard deviation, so we square it to get our variance. So we have each variance added 4 times. We get 0.0256. Then we take the square root of that to get the standard deviation of 0.16. So we now have the mean of 8.68 and standard deviation of 0.16. So now we get to use standardizing the score and table A to determine the probability. We have our illustration here showing what the distribution looks like and the area under the curve that we want, right, between 8.5 and 9. Right. We get a lower bound z-score, 8.5 minus 8.68 all over to 0.16. We get negative 1.13, and the upper bound, 9 minus 8.68 over 0.16. That's going to give us 2. So we find the probability of z being greater than or equal to negative 1.13, less than or equal to 2. We look these things up on table A. We get 0.9772 for the proportion under the curve less than or equal to 2. We get 0.1292 as a proportion under the curve less than negative 1.13. So we subtract that from 9772. get 0.0, which means there is about an 85% chance Mr. Stearns' tea will taste right. So again, this is going through the same type of normal distribution process, standardizing the score using table A that we've done with several different types of normal distributions, performing those types of calculations. So this is, again, more practice with that. You can see it's not going to go away. Thus concludes section 6.2 on transforming and combining random variables. All right. Today we learned how to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. We learned how to find the mean and standard deviation of the sum or difference of independent random variables, and we learned how to find probabilities involving the sum or difference of independent normal random variables. That was today. And that's all. That is the presentation. So now, is there any questions? Anything I can show another example of? Anything you'd like explained in further detail? Anything like that? All right. So then I recommend that you take a look at the practice problems for section 6.2 in Canvas. Try a couple of them, see if you understand how to do them, see if you can get the right solutions. Obviously, it's not homework. It will not be collected. It will not be checked for accuracy. The solutions are provided along with the practice problems. It would just be a good idea to try to see if you understand the things that we did today. There's also extra worked examples. Please take a look at those. And if you have any questions, please let me know. Email me, send me a message on Teams. Do what you can to get a hold of me. I'm happy to help. Other than that, that is the lesson for today. I'll see you guys tomorrow, right? Same time. Have a lovely day. And yeah, that's it. That's the lesson. That's what I got. Enjoy the rest of your day.